All right, welcome. In this video, we are going to discuss combination and decomposition reactions. So you should either be watching this video if you missed class on the day that we discussed this, that was on a Friday, or you can also be watching this video as a review later on, just to make sure you're feeling confident in this material. So first of all, I want to do a quick review of just what we mean by a chemical reaction. So we write out an equation for a chemical reaction. It would look a little bit like this. So this is, we call this a, oh, my stylus is not working. Here we go. So this would be a chemical equation for a reaction. And the stuff on the left-hand side of the equation is called our reactants. Those are the things that we start with. And then over here on the right-hand side, those are the products. That's what is made during the reaction. The arrow indicates the change that is occurring, that your reactants are turning into products. And we see these little symbols represent states of matter like liquid and gas. These coefficients out in front, these are called coefficients, those numbers out in front. We'll talk more about how to determine what those should be later on when we go over balancing chemical equations. But what we're going to be focusing on today is we're not going to worry about what the coefficients should be. We're going to focus on identifying certain types of reaction and predicting what the product should be of those types of reactions. Coefficients we will deal with later on. All right, so there's three main types of reactions we're going to discuss. That's combination, decomposition, and combustion. So first, let's take a look at combination versus decomposition reactions. So in a combination reaction, you have two or more substances combining to form a single product. In a decomposition reaction, you have one reactant that's broken apart into two or more things. So that's a general overview. So I tend to like to visualize this as combination reaction is two things combining to form one thing. Decomposition is one thing breaking apart to form two or more different substances. So they're kind of opposites of each other. Another thing to be aware of when we are writing out equations for reactions is there are 7 molecules that we refer to as the diatomic molecules. And that's H2, O2, F2, Br2, I2, N2, and Cl2. That sounds like a lot to remember. There's a fun word we can use to remember that. That's Hofbrinkel. So just keep in mind Hofbrinkel. That tells us the elements that come in pairs. So that means that if someone says, oh, I've got some oxygen gas, oxygen always comes in the form of O2. Or if someone says, I've got a sample of pure hydrogen, hydrogen is also a gas, it is H2. So those elements are always diatomic. Any element that is not part of Hofbrinkel, like if someone says, oh, I've got a sample of aluminum, then I'm just going to write down Al. So the symbol for an element will either just be the element by itself, or if it's part of Hofbrinkel, you're going to put a little subscript 2 by it. And that means that the little subscript 2 tells us that there's 2 H atoms bonded together. So that 2 tells us there's 2 oxygen atoms bonded together. All right, so we've done a little background. So now let's do a practice problem here. We've got 2 reactions here. Highlight the combination in blue and the decomposition in pink. So let me go over here and get my pen. So combination is going to, combination we're going to put in blue. Okay, so combination is going to look like this. 2 things combining to form one thing. So that looks like this one looks like a combination reaction. And then in pink, decomposition is when one thing is breaking apart. So the decomposition reaction is this one right here. So that's just identifying reaction types. And now we're going to use this knowledge to actually predict products of a reaction. So when we're predicting products of a combination reaction, you can think CCC, combination equals crisscross. So whenever we're doing a combination reaction, we're always going to be looking at, all of the reactions we'll look at will be forming ionic compounds as a product. And you might remember when you're trying to figure out the formula of an ionic compound, like let's say you want to figure out the formula of aluminum oxide. So to figure out what happens when aluminum and oxygen come together is you would take a look at what's aluminum and what's its charge. Remember, we can look at the periodic table for a reminder of what ion charges these things will form. And then oxygen, take a look at what its ion is and its charge. And then you are going to crisscross to figure out what the subscript should be. So aluminum oxide would be Al2O3. So when we're predicting products, we're going to find that all of our products are going to be ionic compounds. And so to figure out the formula of the ionic compound, you got to do a little crisscross here. All right, so let's try one. So we write the chemical reaction for when solid sodium reacts with chlorine gas. I'm not going to worry about labeling states of matter right now. If I wanted to, I could add in S for solid and G for gas, but we're just going to focus more on what's the product going to be. Okay, so my reactants are sodium and chlorine. It's a combination reaction. And so when they come together, I'm going to take a look at the charge of the ions. So sodium, I look at a periodic table. I'm going to say sodium has a +1 charge. Here's sodium right over here. And then chlorine over here has a -1 charge. So right now, the charges add up to 0. So if the charges are already the same, like +1 and -1, I don't even need to do any crisscrossing. I just need 1 sodium for every 1 chlorine. So hooray, I'm done. Okay, this is my formula here. Another way you can think of it is you could also think of it as, oh, I crisscrossed it and I ended up with Na1Cl1. And so we tend to just not write the 1. So if you got 1 of each, you just write NaCl. You might be thinking to yourself, wait, how come there isn't a 2 here? I thought you said that chlorine is diatomic. There always should be a 2 there. Well, that diatomic thing only has to do with chlorine when it's by itself. So chlorine on its own is always going to be Cl2. But when chlorine's in a compound, it could take all different forms. So it could just be NaCl. It could be like if chlorine bonds with aluminum. Well, we'll see what happens there next. But so the diatomic rule only applies when you have chlorine by itself as an element. When it's in a compound, the way you figure out the subscripts in a compound is by looking at the charges of the ions. All right, so now let's try another one. Let's look at solid aluminum reacting with chlorine gas. All right, so it's going to combine and form a product. So the product is going to be aluminum and chlorine coming together. So I'm going to look over here at my periodic table to find the charge of these ions. So aluminum makes a +3 ion, chloride makes a -1 ion. So aluminum's +3, chloride's -1. So if we do a little crisscross, the 3 goes down here, the 1 goes down here, and I'm going to go back and I'm going to erase these charges because now we have a compound. My compound overall does not have a charge. And then we said we usually don't write the 1, so I'm going to go back and erase this 1 there. So there you go. So that is my product. You might notice right now, it might bother you the fact that there's only 1 chlorine over here and there's 2 chlorines on this side, and there's 3 chlorines here and 2 on this side. That's okay. These numbers do not have to match. It's not going to be the same on the left and the right. Later on, we'll come back to this idea of balancing. So we'll come back and we'll balance these using coefficients. But we're going to do that later. So our first step is we just want to be able to figure out what the products of this reaction are going to be. And then later on, we'll worry about what the coefficient should be out in front. All right, so we do, here's another example of a combination reaction between magnesium and oxygen. And this is one that we will do in class. So you may have seen this. So magnesium and oxygen, when they combine, it's fun. It releases a lot of light. And when they come together, the magnesium and oxygen, you're going to look at your periodic table and look at the charges. So magnesium's over here. It's got a +2 charge. Oxygen's over here. It's got a -2 charge. So your magnesium's +2, your oxygen's -2. You do a little crisscross, you end up with Mg2O2. So that simplifies to Mg1O1. So it's just MgO. That is my formula, is just MgO. There we go. So now let's look at decomposition reactions. So this is the opposite pretty much. So in this case, we're starting with 1 reactant. So like we're starting out with aluminum chloride. And then that reactant is going to split apart into its elements. So aluminum chloride is going to split apart into aluminum and chlorine. So first I'm going to just write down the symbols of those elements. So I got aluminum and chlorine. And then I'm going to go back and actually I'm not going to do this in cursive because I think that threw off people before. Okay, I won't use cursive. Al and Cl. Okay. So this is my aluminum and chlorine. And then whenever you are writing out the formula or the symbol, I guess, for a element, you want to ask yourself, is it part of Hofbrinkel? Okay, so if the element's part of Hofbrinkel, you put a subscript 2 by it. If not, then you just leave it be. All right, so aluminum is not part of Hofbrinkel, so I'm just going to leave it be. Chlorine is part of Hofbrinkel, so I'm going to put a 2 right there. And if I want to label states of matter, this is going to be a solid, because it tells us right there it's solid. Most ionic compounds are going to be solid at room temperature. And then actually, if I'm trying to figure out states of matter of my elements, this is actually color-coded to tell me the states of matter. So when we're looking at this one, on this periodic table, blue is the solids, red are the gases under standard conditions, and then the green are liquid. Notice not very many of them are liquids at room temperature. We have a big periodic table in the classroom that is also color-coded, but the colors are a little bit different. In the classroom, the solids are marked with black, and then the liquids are blue if you're looking in the classroom. So different color coding, but still wherever you are, you'll be able to look at a periodic table and kind of figure out the states of matter from there. So it looks like chlorine is red and aluminum is blue. So that means that aluminum is a solid, chlorine is a gas. All right, now let's look at K3N. So potassium nitride, it's going to break down into its elements, K and N. And then ask yourself, are they part of Hofbrinkel? So K, not part of Hofbrinkel, so it just stays K. But N is part of Hofbrinkel, so it is diatomic, which means it's N2. And if I look on my periodic table, I would notice that K is a solid, and then N2 is one of my red gases. It's not actually red, but just, looks red on the periodic table. All right, so those are our two types of reactions so far. We've got combination reactions where two elements come together to form a compound. And then we've also got decomposition reactions where a compound breaks apart into elements. Third type of reaction is combustion. So this is when you have a substance that reacts with oxygen. That is the basic definition of a combustion reaction. So let's highlight the ones that are something reacting with oxygen. So this one looks like a combustion reaction. It's reacting with oxygen. The second one is not. I don't see any oxygen over there on the left. This third one looks like a combustion reaction. So does this one. It's something reacting with oxygen. And so does this one right here. So what these highlighted ones all have in common is notice oxygen is one of your reactants. And 3 of the 4 reactions follow this general format where you have a hydrocarbon, meaning something that contains, notice how these all have carbon and hydrogen. We call those hydrocarbons. They've got carbon and hydrogen in them. Reacting with oxygen, and the products are CO2 and H2O. So that is something that is common for combustion reaction. So when you think of like burning wood or burning paper, or burning propane, it's going to follow this general format. We're making carbon dioxide and water. The one that doesn't really fit is this one right here. So, but this, we can still call this a combustion reaction. We also could classify it as a combination reaction because it actually fits both definitions. So it's something reacting with oxygen, and it's also 2 elements combining to form a compound. So it actually could be classified as both. All right, so keeping this in mind, let's try and make a prediction. Let's predict the products for the combustion of CH4, which is methane with oxygen. So CH4, methane, reacts with oxygen to form, well, what does it form? Well, all of these combustion reactions make carbon dioxide and water. So if you got something that is we call this a hydrocarbon because it contains hydrogen and carbon, reacts with oxygen to form carbon dioxide and water. That is the general format of a combustion reaction. So let's try another one. This is octane. This would be like what's happening in the engine of your car. So octane plus oxygen makes CO2 and H2O. So really, combustion reactions are the easiest ones to predict the products for because the products are always going to be the same no matter what. All right, and I'll stop this video here and I'll make a separate video going over these sample problems at the bottom.